Hey everyone, welcome back to discussion 24. We're looking at page 480, problem 4. Okay, so the first few problems are a whole lot of what we call plug and chug, and that's pretty much just we apply formulas and then see what comes out of it. Okay, so we're given a function of position for an oscillator, and we're asked to find the position, velocity, and acceleration at 3 different times. So we want y, we want v, we want y, v, and a at 0, so it's t equals 0, at t equals it's 1/2, and then t equals 2 seconds. So we want y at all of these, we want v at all of these, and we want a at all of these. So first thing we need to do before we can plug these in and just start going is we actually have to find v and a, right? So dy, it's not a vector, dy of t dt is equal to v of t is equal to 10.4 times 0.85 meters. This is negative sine 10.4 t minus 5.2. Okay. Then d. Now what do we have here? So we'll say d squared y of t dt squared is equal to dv dt is equal to a of t is equal to negative 10.4 squared 0.85 meters cosine 10.4 t minus 5.2. Going kind of quick because this is just a lot of writing. Okay. Notice that in our initial equation, 10.4 is here. This is for a standard form where you have the amplitude, right? So we call it y max is our amplitude times cosine omega t minus a phase shift. So omega in this case is 10.4. Now notice this. The only thing that came out of this derivative is 10.4, right? Negative 10.4. Then we had negative again, 10.4 squared. So roughly speaking, let's take this down here so I don't have to rewrite it. And this is in your book too. So this is something that you can check out in the book. Okay? So roughly speaking, we have these relationships. Sorry, this one here, this is important. This one here is only true for t equals 0. Right? So otherwise this is not equal to this. So this one is true all the time. This one is actually, you end up with y max sine omega t minus phi, right? Okay, so now that we know also y max, our amplitude is 0.85 and our phase shift is 5.2. So we have all of the information that we need, right? So y max is 0.85, amplitude shift is 5.2, omega is equal to 10.4. Okay, those are given. So now we just plug in for 3 different values. So let's take 0. Y of 0 is equal to 0.85 times cosine of negative 5.2. v of 0 is equal to negative 10.4 times 0.85 times sine of negative 5.2. A of 0 is equal to negative 10.4 squared times 0.85 times, well, we can just take, this is y of 0, y of 0. I guess we could have done this as y of 0 as well, but yeah, we can, actually. Let's just do that. No, that's a different value, excuse me. Okay, we'll just leave it the way it is. Okay. Okay, so after plugging in these values, plug in this, you get these values. All of this gives you this, and so on. So that's 0. That's part A. Next, we do the same thing for y of 1/2. That's going to be 0.85. Now we don't, well, we need to consider this as well, right? So that's going to change things a little bit. Negative 10.4 times, what do we have? 0.85 sine of 10.4, 1/2, minus 5.2, right? And then A of 1/2 is equal to negative 10.4 squared y of 1/2. Yep. Okay. Okay, so I plugged in further for the 1/2 second. This is actually, my units are a little bit backwards here. This is meters per second, this is meters per second squared. We know that because this is given to us in meters in the problem. So make sure you check your units. Okay, anyway, so now look what has happened. This goes to a new position. That's expected. This goes from a negative velocity to 0, so that must mean we're turning around, right? And our acceleration has almost doubled, almost. So yeah, so that means that we're probably at some point up here. So if we have an oscillating system, right, we're probably somewhere in this vicinity right now with 1/2 second, because the velocity has gone to 0 and the acceleration has gone up. Okay, so for the next part we do the same thing. Y of 2 is equal to 0.85 cosine 10.4 times 2 minus 5.2, right? And so on. Just going through the calculations. This is 10.2 times 10.4 times 2 minus 5.2. Okay, and then A of 2 is equal to negative 10.4 squared times y of 2. Okay. Okay, again, I have gone through and plugged in the numbers, and you'll notice that for part B, we had a value which was our maximum amplitude, and then for part C, we also have a value which is our maximum amplitude. And the value of the the value of the velocity has gone down almost to 0, not quite, 0.1, or it's about 1 meter per second squared. So it's decreasing, right? And this is the same as this here too. So that's interesting to note. So we are oscillating. I would expect this to be a little lower, but this is what we get when we plug it in. Okay, for number 6, I'm not going to walk you through all of these because that's just kind of boring and it's unnecessary. But I will take the derivatives of the functions and get it set up. So we're given the exact same function for position. So let's just steal this. And then we're also asked to find sorry, we're not actually given this as a function of position. We're given it as a function of acceleration, so we need to change that, but pretty much it's the same, right? So this is going to be in units of meters per second squared. Okay, and then again, it asks us to find the position, velocity, and acceleration at each of the following times: 0, half second, and 2 seconds. Okay. So what we need to do is find velocity and position functions. So we have to integrate. So the integral of a of t dt is going to give you the function velocity. Velocity is a function of time. Right? Great. So you could use a substitution method where u is the argument inside the cosine function, 10.4t minus 5.2, and du is equal to 10.4 dt, right? That means that 1 over 10.4 du is equal to dt. So you could go through all of this and do that. So it's not a bad idea if you're not super comfortable with taking an integral this way. I recommend it. What I'm going to do is write down what I get. Right? We're integrating this cosine function. So that's just going to give us a sine function. And this, notice that this is not negative. So it's 1 over 10.4 times 0.85 meters per second times sine 10.4 t minus 5.2. Okay, for the next one, we do pretty much the same thing. You can use the same substitution, and you're going to end up with a very similar, well, an answer that you would expect, let's say. We're going from positive sine, we're integrating, so that's going to give us a negative 1 over 10.4 squared, 0.85 meters per second, cosine 10.4 t minus 5.2. Now notice that we still have a relationship. If you look at this acceleration function, we still have the relationship that this is equal to negative 10.4, excuse me, negative 10.4 squared of y of t. Right? That still holds. So that's good. So I think we're on the right track. All right, and then you just take your functions and you plug in the values that you're asked to plug in. So I'll just do it in order. Since I went through and found them, I'll just make this a little more organized just so that it's less confusing. Right? So this is what we have. And then you take each of these functions and you plug in y of 0, y of 0.5, y of 2, v of 0, v of 0.5, v of 2, a of 0, a of 0.5, and a of 2. And then you write down what your answers are. So I've gone through and plugged in all the values, and it is interesting to note that we do have oscillations again, which is what we would expect from an oscillation function. So notice here we have a value of negative 0.008, and here we have a value of 0.008. So at half second and 2 seconds, we're oscillating between the same value. And the velocity is essentially 0 as well. Yeah, so we also have an acceleration of 0.85 meters per second squared and negative 0.85 meters per second squared here at 2 seconds. Okay, and then this would be due to the offset, right? Because we have some initial phase we have some initial phase offset. So that's going to give you a value here. That's at this point, we are going to have some answers. Okay, anyway, next problem. So the next problem, we're given some information. We have an amplitude of 4 centimeters, which is also the y max. We're told that V max is equal to 10 centimeters per second. We're also told initial phase is 0. And then we're asked to find position when the velocity is equal to 4 centimeters per second. That's part A. Part B asks us to find velocity when the position is 2 centimeters. Okay. Okay, since our initial phase is 0, this is going to make some things a little bit easier, right? So this is going to be, our general form is this, right? Omega t minus phi. Well, this is 0. We know what this is. So we already know what y of 0 is. It's y max, right? So y of 0 is equal to y max. Is equal to 4 centimeters. Okay, that's useful information. Let's, we can also consider that for some v of t, we have negative, for pretty much any v of t in an oscillation problem like this one, we have v is equal to negative omega times y max times sine omega t. Right? Because our initial phase is 0, so that throws that away. Throws the phase away is what I'm saying. And then, so now, what we can consider is this is actually our maximum velocity. If this is the maximum position, then this term here is going to be v max. And we're also told this in some examples in the book, which I recommend looking at. Okay. So now, our oscillation speed is V max over Y max, which is equal to 10 centimeters per second over 4 centimeters. Is that right? Yeah. And that gives us a value of 2.5 radians per second. So that's another thing that we can actually use, right? So now that we have this information, we can just plug it into a function. So we're told, for part A, we're told that velocity is equal to 4 centimeters per second. So let's just plug that in and see what that means for us. Negative 2.5 radians per second times, what was it, 4 centimeters, right? Times cosine 2.5 times t. Right? That's radians per second times seconds. Okay, so, well, the only thing we don't know in this equation is t, so we just have to solve for t. So that gives us 2.5 times 4 cosine 2.5 times t, right? So then this is just, I mean, I put all my units in here. This is just a simple version real quick so that we can solve. So, well, we have a 4 over here and a 4 over here. So we have 1 over 2.5 right? This is going to be arc cosine. And then we also have 1 over 2.5 here. That's going to equal t, I think. I should be careful because this is a velocity function, so we should actually have a sine term here. So that's important. So I was going a little fast, and again, I dropped. This should be sine, not cosine. So this is sine. And again, here, this is arc cosine. Okay. So plugging this in is going to give us a value, let's call this T5, 4, just because the initial velocity was 4 centimeters per second. This value comes out to be negative 0.16 seconds. So what I want to do is just take it to be positive. I'll show you what I mean. We're told to take this value. We want to know what the position is at this time, right? That's pretty much what we're after. We found the time, so at the time when this is 4 centimeters per second, solve for that time, gives you this. We plug it in and we find the position. What position is it at that time? So that's equal to 4 centimeters cosine 2.5 times negative 0.16. And what we end up with is 3.68 meters. And so you can plug this in, and you can try this, and I encourage you to try this. So you plug a negative 0.16 in, it gives you the same as 0.16 because this is a position function. Sorry. Because this is a cosine function, not a position function. Because this is a cosine function, this is an even function, right? So this is going to come out to be the same no matter if this argument is negative or positive. So that actually works out pretty nice for us. So you can plug that in, and that works. Okay, and now we want to know for part B, what is the velocity when the position is 2 centimeters? So we do pretty much the same thing. 2 centimeters is equal to 4 centimeters cosine 2.5 times t. Solve for t. So this is going to be 1/2. Let's do this. Cosine inverse 1/2. 1 over 2.5. So that gives us a value of 0.42 seconds. It's a good thing it's positive because we're going to plug this into our velocity function, which has a sine argument, and that will not take a negative value. That does not equal the same thing, is what I'm trying to say. So here we take 0.42 seconds. This is going to equal, now what is our velocity function again? Right, of course it's negative omega times 4 centimeters. This is centimeters per second, that's the units of omega, and then it's going to be times sine 2.5 times 0.42 seconds. So that comes out to radians, and this gives us a value of negative 8.67 centimeters per second. Okay, next problem. Problem 22, page 481. Okay, so we are given, for the next problem, we're given a spring system where this block is resting between two springs with spring constants K2 and K1 respectively, right? We know the general form of oscillations, the oscillation speed for a spring is given to us is square root of K over M, right? That's standard, and you can look that up pretty much anywhere. It's definitely in the book. Okay. Okay, well, what we're asked to find is an expression for the angular frequency of oscillations of the resulting simple harmonic motion after this thing was displaced, right? So we have an initial displacement. We'll call this x naught, and this is x equals 0. X equals x naught, right? That makes sense. So this is 0, that's x naught. Okay, so what we want to do is consider what we know about springs. Well, we know Hooke's law, right? That's a force is equal to the negative spring constant times the displacement, right? In this case, we're going to have negative k times the displacement is x naught in the positive. We'll call this the positive x hat direction. Okay, so this is k x naught, sorry, k1 x naught for this spring, right? K1. So we're finding the force of this spring. This spring is going to exert. Is k1 x naught. Okay, and then for spring number 2, negative k2 times, again, the displacement is from 0 to x naught. So we only have one block in the system. If there were 2 blocks in the system, it would be different. We would have like this one and another spring and another spring, and then these would both be moving opposite each other, and so you would have negative positions. But right now we're just displacing it in the positive x hat direction, so this is also x naught. So now we just sum these up using what we know of forces, right? F net is going to be equal to negative k1 x naught minus k2 x naught. That's convenient. So now we have negative k1 plus k2 x naught. So now the total force, the total spring force on this system is given here, right? This is the total spring force on the system. Okay, so what we have is we've just summed up the spring constants. So this is going to be, we'll call this an effective. We can always call this like k effective, right? Which is equal to k1 plus k2 x naught. That's your net spring force. So now we can use this theorem here, this little piece of theory. Omega is equal to k over m. What we have here is we want to know the oscillations for the system, right? That's what we're asked to find. What is the resultant oscillation of the simple harmonic motion? Well, we can use the k effective that we just found from the force. So that's going to be k1 plus k2 all over the mass of the block. And that's your answer right there. Okay. There we go. So that's what you get. Okay, problem 32. A simple pendulum is constructed from a bob of mass m with 150 grams and a lightweight string of 1.5 meters. What are the periods of oscillation for this pendulum? Okay, and we're given 4 different scenarios. So we want to know when it's just sitting in a physics lab at sea level. So like in the physics building at UWM. We want to know what is the period of oscillation in an elevator when it's shooting upwards at 2 meters per second squared. We want to know what is it when it's in an elevator shooting downwards at 2 meters per second squared. And then finally, we want to know when it's in a school bus accelerating horizontally at 2 meters per second squared. Okay, so here we just have a simple pendulum. Right, that's what we're told. It's oscillating back and forth. It has a mass. Try and get this. Come on. Okay. So we know that for a pendulum, again, this is a very basic identity that is given in the book. We have G over L. Or let me just double check that. It might be L over G. I think it's L over G. Nope, G over L. So I was right. Good. So for a simple pendulum, this is what we have. This is how you find its oscillation speed. Okay. Now we also know that omega is equal to 2 pi for rotational kinematics, right? Over period. So what we're asked to find is the period. So then we would have to equate this with 2 pi over t, which then gives you t is equal to 2 pi L over G. So that's what we would use. So that's what we're going to use for each thing. Now notice that in here for a simple pendulum we have G. But G is the magnitude of the acceleration for the surface of the Earth, right? And so what we're going to want is we want the magnitude of the acceleration for each situation. Whatever its components happen to be. Shoot. I think it's messing up. So here, for whatever components we happen to have for each different acceleration that we're given, we just need to plug this in instead of G. So for part A, nothing has changed. The acceleration is the acceleration at the surface of the Earth because it's in a physics lab. So this period of the pendulum is going to be 1.5 meters over 9.81 meters per second squared. Okay, that's the first one, and that's going to give you a value of 2.46 seconds. Okay, now let's recall that what I just talked about regarding plugging in the magnitude of the acceleration vector for whatever situation we're given. So we want to use t is equal to 2 pi for the next parts, by the way. This is correct for part A. So part A is done. We don't need to worry about that. But for the next part, we want L over A. Okay, so now we have an elevator accelerating upwards at 2 meters per second squared. So what this gives us is our acceleration is going to be, now we have 9.81 meters per second in the y-hat direction, right? And we're told that this elevator is also accelerating upwards at 2 meters per second squared, which means that you're going to feel an accelerated force pushing down, right? So we're going to say that that's going to be the same thing. So negative 2 meters per second squared y-hat direction. So now the magnitude of this is going to be negative 11.81 meters per second squared. We plug that in to our equation, 1.5 meters, 11.81 meters per second squared, and we get a value of 2.24 seconds. That's the period that that's the period of the pendulum on that elevator accelerating upwards towards space. Okay. Next part, we're told now that the elevator is accelerating downwards. So the pendulum is here, right? But let's say you're on an elevator accelerating downwards. You're accelerating downwards. The Earth is pulling you down, right? So there's a gravitational force pulling you down. But because this thing is falling from under your feet at 2 meters per second squared, it's actually opposing. You're actually going to have an opposing acceleration. So we have here negative 9.8 meters per second squared y-hat. So now we have positive 2 meters per second squared in the y-hat direction, right? Because if this one was pushing up at you and you're feeling a greater acceleration, you're actually going to feel 2 meters per second squared less acceleration if the elevator is dropping out from under you at that speed, or at that accelerated rate, right? Anyhow, the magnitude is 7.81 meters per second squared. Okay, and so we plug that in. 1.5 meters. That's the length of the pendulum. 7.81 meters per second squared. This gives us units of seconds, and it's 2.75 seconds. That's the period. Okay, next part. We're told, so let's draw our acceleration. Let's write it out. Right, this is meters per second squared, y hat, right? That's our acceleration vector. But we're told this is our normal acceleration vector, excuse me. Now we're told that we're moving on a school bus, accelerating horizontally at 2 meters per second squared. So what we want to do is just say this is going to go positive 2 meters per second squared in the x hat direction. Or rather, excuse me, we'll call this now z hat because we're not talking about a two-dimensional image. What I mean by that is this. Just quickly draw this out for you because I don't want to confuse anyone. So the bus is traveling that way. Okay? We'll call this x hat. Alright, this would be negative y hat, and this is z hat. Okay, gravity is pulling you this way. You're also being accelerated this way. So you're accelerating this way and this way. Okay, so we just need to take the magnitude of this vector. So that gives us 9.81 squared plus 2 squared, all under a square root. Gives us a value of 10.01 meters per second squared. And then we plug that in. 2 pi 1.5 meters, 10.01 meters per second squared. That gives us a value of 2.43 seconds. And that's your answer. All right, thanks.